Right, everyone. Welcome to another life science session here with Dugan and Nick. We're going to be talking about Cubix algebra. So I wanted to basically advertise that we have a little function that we put together, and Nick very expertly cleaned up and now can be used is in the repository, so you can just use it yourself if you want. And I thought what I would like to do is to go
Wait,
over.
it is already published?
It is published, isn't it?
I don't know.
I think it was published. I published it, I think.
Well, it has to go through curation. Has it been curated?
Oh, maybe it was not published. Maybe I just gave an announcement of a future happening, not a present state of affairs. I thought I mean, sorry, it is submitted. I don't know if it's published, but it is submitted, right?
I guess, but they
Yeah.
haven't responded, right?
Okay. I don't think so. No. I mean,
Okay.
I don't know how you check those notifications, but
Just by mail, I guess.
yeah, I guess not, because the mail would be my institute mail and I didn't get anything. So yeah, so it is not published, it is submitted, this will be out there soon, but anyway. So what I thought could be interesting to do today is to go over the Cubix algebra kind of basics that I think we have discussed before, but I don't think we had a live stream on this specifically. And just use the function to illustrate, kind of visualize these abstract objects and how they are being operated. So it should be a very kind of just explanatory session. There's more like I'll walk you through some of these algebraic things, and if anything catches your attention, we can focus a bit more time on it. But let me share this notebook. So I guess I'll make it a bit bigger. All right. So what are we looking at here? So we want to deal with what I call arrays, right? So arrays, as you know, in Wolfram language, this is just some generalization of tables or matrices. So in principle, you just have a collection of indices that have values and that range over them. And the game here is to try and generalize what operations make sense for these objects. So I want to show. So here are some examples of. So I put together these convenient functions to generate the arrays that I want to generate and I want to deal with, just in a very specific way, because these are just a random integer between -2 and 2, just for some examples, and complex numbers and so on, just for the specific applications that I have in mind. But effectively, these are just generating some like tensors in Mathematica in the usual way. So right. So for example, if I generate, just to understand this sort of generate array function, I can say Boolean values and have it be a 4. So this is dimension. So this is order 4 dimension 2, right? So this is a 2 by 2 by 2 by 2 array. Similarly here, this is a 4 by 4. This is order 2 dimension 4 matrix. And so the whole point is that we have now we can take this thing and whole thing that Nick and I did was we can now do Cubix form. And so, and I have to say, well, I'm just saying to check maybe quicker. So you have something like a 2 by 2 by 2 by 2 integer array here in matrix form, and now in Cubix form you have it basically you align things in a cube, right? So the same way that by default this arrays things in a square or in a rectangle, this will align things in a cube or in a sort of parallelepiped, right? Like you will have it that way. So for example, let's look at some proper, for example, this one. So Nick, what was the, I want just have it. What was the option here in Cubix form?
I don't know. It was
mean,
like 2 weeks ago. I don't remember already.
Yeah. So let me just check.
Just ask for options of the Cubix form.
But it
to
wasn't.
have-
It wasn't an option. It was something that.
Was it in the documentation that we wrote? Just open the
I have it. I
this.
have it here. Yeah. So I think, but I think it's at the end. Yeah. It's at the end. No, wait. No, actually, it's not in the documentation. So the item size is what fixed the. Oops, I think. Not what I was getting that error. I have this here. Yeah, this error, I don't know why I keep getting that, to be honest, but I don't think it's any of the options, is it? Wait, indices.
What's the issue?
The issue is, so annoying, that we want, so for example, if I do this, it basically, since the values are Boolean already, it puts a frame around the frame already.
Mm-hmm.
So
But the frame is a fixed like width, and it's not displaying correctly if the thing inside is bigger than the width of the frame.
yeah. I mean, the point is that the frame is emulate. So this is the frame inside is this frame, is that sort of finite field
Yeah,
graphics thing
that little box.
that we use by default here because it was neat. We liked it graphically. At least I did. And then, but Nick, you said that it's okay not to have it as an option, just disable it when you want to use it. I remember you saying that, but I can't.
No, there's the item size. I just look for examples. I think I had your example somewhere, maybe.
No, that's what I remember. But actually, the only one that we had was the longer, so the clipping one. This one in this on the screen.
Item size.
No, but
So
that's just the item size, right? It's not the box. Well, let's just not use Boolean just for the sake of this live stream. But basically, I think if you remove the option, this framed. Oh, framed. Oh, maybe it's framed. I think that's it.
yeah.
Oh yeah. Sorry, that was stupid. Yeah. So anyway, apologies for that. There was an option. I was just blind, apparently.
I guess you could
so-
set the default to false, and then you won't have to.
No, it's good that I think it's good that it defaults to true because you normally are dealing with integers or otherwise non-finite field elements. So behavior is fine. Anyway, so as I said, yes. So you have this kind of thing where you have like a Boolean 2 by 2 by 2 Cubix in this case, and you have this thing. So that's why we call them cubices, right? Or Cubix. So it's cubic matrix, short for cubic matrix. You have these shapes. So I can show you some options here. So for example, you can do plot theme dark. And then it basically gives you a dark theme. We could show the, I guess, indices. So obviously this graphic doesn't have any information about the indices explicitly, right? So you don't know, just by looking at it, you don't know what is first index, second index, you just know it's kind of a cube. So if we say numbered, we should get the same thing, but if we say, because that's just the numerical values, but if we say colored, we get a color code for the indices. So if you really, so RGB is 1 to 3, and it's always 1 to 3 because it's always a Cubix. So if you really want to see the indices, then you just invoke the nomen. So this is by default false. And then that way you can see a little sort of axis origin that tells you which directions are which index. And that should uniquely identify, this position here is the 1, 1, 1. I mean, also you have mouse over. This is very useful. You can use your mouse to check what the coordinates are in your elements. And then you can also copy the element, right? So that works pretty neatly, which, it's like when you try to copy like an element here in the matrix. So same thing, but copying it in the graphic. So it's pretty neat. It's quite a useful thing if you're doing computations with QBCs by any chance. All right, so today's live stream, I wanted to be quite short and to the point, mostly just displaying some of the operations, some of the phenomena that happens in this array algebra. So let's, for example, so what are some special arrays? So of course, we all know from linear algebra, you have a matrix, you have basically two special matrices, or maybe three. You have the zero matrix, you have the all ones matrix, and you have the diagonal ones matrix, so the identity matrix, right? So these are easy, very easy to generalize to higher order. So, zero array, that's the obvious thing. The one array, it's the obvious thing, it's an array all made of ones. The identity array, well, that's perhaps not so obvious how to generalize, but basically you have only ones in the diagonal. So this is, for those familiar, this is the Kronecker delta symbol, delta I, j, k, etc. That's what the identity array is. But most interestingly, you have what I call partial identity arrays. So these are arrays that have sort of identity arrays in some subdimension. So in particular, so let's have a look at the identity arrays, and I call them identity arrays generically in just for short. I don't want to say partial identity. So if I say an identity array, I might mean some of the following. So let's see which ones we have. So we have in matrices we have only one, right? The only identity array is the identity matrix, the usual one diagonal matrix. But when you are on QBCs, so n by n by n, there are there's more than one. So let's see what we have. So we have so what do you say? You say a partial identity is defined by some indices on which you are an identity, right? So this one, so for example, so let's do first the partial identity array of, and now I'm going to do Cubix form by default.
There's like a new thing called symbolic identity array and symbolic delta product array. I wonder whether they're related to this thing.
Symbolic?
Yeah.
Delta?
Symbolic delta product array.
What are the arguments here?
Check the documentation because I have no idea. So it's, but maybe it's relevant.
Where did this open?
In the first argument is like a list of dimensions, and then you specify. Let me just check the first example. Produces. I don't think it's like I don't think it works like your partial array, but it's some sort of identity.
Um, that's weird. Let's check this example. So can I get this thing and put it into Cubix form?
You can do normal and then Cubix form. Because it's symbolic, just a symbol, but then you can turn it into an actual matrix.
Aha. Interesting. I actually want the matrix form for a second, just for my intuition. Represents, okay, so those are the dimensions, fair enough. Arrays with elements, AI, etc., equal to 1 if I oh. Interesting.
Also like a product of Kronecker deltas.
Right. Delta product.
So if you specify 1, 4, 2, 3, it's like you're putting ones where 1, 4 times 2, 3. Weird. Yeah.
Yeah, so let's see, this one represents interesting. So if I do symbolic delta array, no, wait, no, symbolic identity. Let's say 3, 3, 3. Make it normal.
I think that's going to be a Cubix of Cubixes.
Ah, interesting. Well, you can see here that we can nest our QCs, at least with this example, accidentally, which is pretty neat graphically, but that is a bit weird. Now, of course, if I do this, then I just get, wait, what?
It has a rank twice the number of dimensions that we have.
Yes, yes, yes. I can see that. Huh. Interesting. So it just maximally skips our identities in a way, because you jump from being, so basically you can have, multiples powers of 2, basically, right?
But identity array is actually useful. I already used that. I'm not sure about the delta product array, but the
No,
identity
I'm
array.
not saying it looks terribly useful to me. I'm not.
Yeah. Well, yeah. Symbolic identity array is just like a generalized identity matrix, right? It's like a product of identities. That's
Yes,
why.
generalized in a specific way. So it was relevant for you to mention this because the identity arrays that I'm generalizing here are different. They're generalized differently, right? So this symbolic identity array actually does not cover the case of delta ijk, for example, right?
I guess.
And I
No.
think, do I have it here? Well, I have it here explicitly for this one, but you know what I mean, right? So basically, this
So it should be ones along like the body diagonal of whatever.
that's
square
that's
or
that's
cube.
this one. Yes, that's this one, right? So you can see it clearly here, right? One.
But can you make that with the delta product array, like with a single argument?
Oh,
Somehow?
interesting.
Have-
What should I?
I'm not sure yet.
I have to put the indices here, right? I need two lists of 1, right?
Yeah. Well, it's like 3, 3, 3. And if you just have 1, 2, 3 as a second argument, then it's kind of close, but not this.
1, 2, 3 just as a list? Wait, I don't understand. No, I need 2 lists, right? Only.
I don't like this. It doesn't have to be 2. It can be arbitrary.
Oh, but you mean just lists 1, 2, 3?
Yeah, but it's not quite it, but at least it's a Kronecker delta.
Why is it not?
Oh yeah, I figured it out. Like this one, just post it in chat. The second one, I think is exactly what you have with the partial identity array.
That's so strange. Wait. No.
No,
Wait,
not
did you
the
just
not this one. Where you have like a matrix form. Scroll down. You had a matrix form for this one. This one. That's it. That's the equivalent to this one.
well? Let's see. Oh, right. But can you? My question really is, can you make this one?
How is it looks like a matrix form? It's a.
Can I look at this in image plot 3D, or you know what I'm talking about? Array plot 3D.
Yeah, this one is the first that I've posted in the chat.
Let's see.
So you can remove the second 1 to 3. It doesn't do anything.
This
Just
one?
1. Yeah, I was just playing around.
Okay. Yes. Yes. So that's very true. So exactly, this is actually a product of deltas. So this I should have noticed this just mathematically. So the triple delta is a product of deltas, where you do delta ijk is the same as delta I1 what I want to say. Yeah. So basically, delta up down delta, with the upstairs and downstairs, and you have ijk and then contracted with some over I prime, j prime, k prime, right? Like, so you have the product of three deltas, basically.
No,
Which is
this is not a product. This is just one delta, right? Because it's a list with a single element, 1, 2, 3. So it's a free argument delta.
I
So
understand,
it's exactly how you wrote it.
No, I know, but the point is, I mean, this time it's a delta product, right?
Yeah. In this case, it's just product of one element.
No, it's not. It's not. That's what I'm trying to say.
It is. Like, look at the definition. It's a expand details on the right. Right? It's a like table Kronecker delta times Kronecker delta, and you go for and the product contains how many deltas that you have, like the number of elements in the second list. So it's just a one delta, free argument delta. So it's the same as yours. It doesn't expand it as a pairs of like two argument deltas or anything like that.
Oh, I see what you mean. I see what you mean. So yes. However, it is true that delta ijk, you can expand it as a product of three deltas.
Yeah.
Right. Okay. Yeah.
You can
So anyway,
try that. Like alternative way of doing the same thing, right? Would be like this, I guess. Yeah, like this. And it's the same array. It simplifies to the same thing, even though you specified it in a different way.
That's kind of, what is this like?
It's the argument for the delta. That's it. It's like the in terms of indices, I guess.
Yes.
So it's like ij, jk, and ik.
Oh, okay. So yeah, so indeed, this symbolic delta product does generalize all these things. But let's look at, so in cubices specifically, right? There are four things that one can do with this. So basically, if you cook up, you try to play around and you see how many ways can I generate three arrays with just deltas, and you want to end up with something that is a Cubix of the same size, then there's basically four ways of doing this. So one way is this one, right? So this is what I call the tridentity. It's a ternary identity, or arity, order 3 identity. And then, so you can see it here as a delta has 1 to 3 as indices. It's just one Kronecker delta, right? So this is the same as saying Kronecker delta, I guess, right?
ijk.
It's not just the arguments ijk, right?
Yeah. And if you make a table.
Yeah.
Yep.
Right. So if I did Cubix form here, I'll get the same thing, right?
Yep.
So Yeah. So anyway, so you have this possibility. This is what I call the tridentity, just for short. And then you can do partial identities. Basically, if you think that you can be a delta, this means being a delta or being an identity in all three indices, right? But because you have pairs of indices, you can be a delta on pairs of these three indices. So you get three choices. So each of these choices has this, sorry, not this, but just delete a bunch of stuff here. Yeah, so this one, partial identity, it means this function partial identity is just defining on which indices are you a delta, right? Which indices are you sort of neutral on? And you have to specify the same thing as an array, right? Like the order and the dimensions. In this case, they're all regular, and so it's just one dimension equal for all the indices. And so if you say partial identity and you say indices 1 and 2, then you get something like this, which is the same thing as Nick reduced up here earlier.
Can you array plot 3D that? So it's yeah.
Well, it's almost the same arguments. It's just it's 1, 2. You also want 2. So it's essentially the same function.
Yes. So this is a useful thing to see. So basically, what this does is you have an identity in each of the diagonals of the cube, the kind of lateral diagonals of the cube. You have one main diagonal. I guess that can also be useful here, right? And this one, let's do.
Right. So this should be the.
Right.
Yeah. So that's like the typical identity that you have for a 3x3x3 grid.
This is what I call the tridentity, which is the direct generalization of the identity. And this is what I call, so this, if you project like this, it looks like an identity on this face, but not on the other two faces, right? On this face or the face behind, it looks like an identity, but not the other two. So basically you have three faces, or three pairs of faces that, in this oriented array. And so you have three indices. So what it corresponds to is what people call broadcasting, right? Like you have an identity matrix, you basically broadcast it in the remaining index. So that remaining index is not doing anything for you. All right, cool. So anyway, so these are just identity matrices. So some useful way to visualize them. All right, so what do we do with arrays? Well, we multiply them together, like we learned in high school to do with matrices. And there are many ways to do this. So the way that
Charles, can you just maximize your mathematical window?
Oh, sure, yes. It's just
and yeah, there.
Yeah.
Cool.
Yeah, sorry.
All good.
So contraction operations are a generalization of what you do with matrices when you multiply them. Back in maybe for some people kindergarten or something, and you learn how to multiply matrices, and then. But now it all becomes a big mess because we have many indices. We don't have an algebra. Sorry, we don't have a linear algebra theory behind covering our backs, telling us this index is covariant, this is contravariant. You should, splice them together so that you get a meaningful multilinear object. We don't have those guidelines because these things are not tensors. These are arrays. And I will never be tired of explaining to people why tensors are not the same as arrays. And again, this is one specific case where this difference makes a world of difference, right? Because if you tell me that my Cubix here, whatever, is a tensor, then you're giving me a lot of information about it. You're telling me, okay, this particular order corresponds to a set of basis elements, and therefore, the indices in this object are all covariant, contravariant, and I know what I have to do. If I change my basis, I know exactly what transformation I should apply to this object. But if you don't tell me anything, you just tell me you have this table of numbers, and it could be a 2-1 tensor or a 0-3 tensor or a 3-0 tensor, or or 1-2 tensor. It could be several combinations. If I changed my basis, you would have no idea what application of the how to conjugate your tensor with inverse basis change matrices or direct basis change matrices, right? So that's one very concrete way to understand that having an array and having a tensor is a very different thing. And all tensors, when expressed in a basis, give you an array, but just an array does not give you a tensor, right? That's the important thing to load up in memory, because everyone calls these things tensors. I don't mind calling them tensors. The languages are always in flux. I'm not attached to the name tensor, but technically these are two very different things. So let's just be clear that that we are dealing with arrays, no multilinear algebra assumed in the background. So because there's no multilinear algebra assumed in the background, we have to invent it in a way. So the point I'm making this.
Wait. So the difference is, for arrays, is just you have like these multidimensional sets of values.
Index
right?
values.
And you're not indicating, and then like a tensor is like you're indicating, okay, sometimes I want this index to be contravariant or covariant, raised or lowered. That is to say, it wants to be paired up with, contracted with other tensors in the future.
Exactly, precisely. So that is kind of perhaps the symbolic justification or the algebraic justification of it, where you say the operations that you are allowed to perform with these objects and how you splice with other objects or compose with other objects depend on how you interpret their indices. But the more concrete technical point is that a tensor, when someone gives you a matrix expression of a tensor or basis expression of a tensor, right, or a vector for that matter, component expression of it, and they tell you this is an element in a vector space and it has this component expansion in this particular basis. Maybe they don't specify the basis, but they say there is a basis on which this happens, right? They are telling you virtually an infinite amount of information, right? They're telling you that you can apply the infinitely many elements of the GL group of that vector space to that one vector, or any amount of vector data that you might have. And if you apply it consistently to all of it, your problem doesn't change at all. Like all your quantities are, all your invariants are preserved and all that kind of stuff, right? So the point here is, if you just give me a array, so it's just an index table of numbers, of scalars, and you just might by default index like all downstairs indices or something, like something like that. If I perform a basis change and you tell me this list of numbers is a vector by default, then I know how to apply the base transformation to that vector. If you tell me this table of numbers is a matrix, then that I know exactly how to apply that. But if
by convention, right? Because you think that a matrix is an array, a two-dimensional array is going to be, let's say, a horizontal list of vertical column vectors.
Yes. But you see, this is not specific
which
to
is a convention, by the way.
order.
I mean, like matrices in Mathematica are rows, right? Or you write them down as rows.
But the point is, the convention is not so important. What's important is that there's more than one option, right? So the point is, this is visible already at the level of matrices. So I don't have to invoke these cubices to make this an issue, right? If I give you a table of numbers, a rectangular array of numbers, it really matters if you're thinking of that, let's say, square. It really matters if you're thinking of that as a matrix. So, sorry, as a linear mapping, or as a bilinear form, or as a co-bilinear form, right? Because in each of these three cases, if you change your basis, your numbers are going to change differently. Like you begin with one single thing, but if you change your basis, if you assume one of these three cases, in general, the matrix you get as a result of the transformation is different. And then you go into different orbits, right? Like generically speaking, you go into different orbits under the GL group, right? So all your invertible linear mappings applied to that thing give you three different families of numerical arrays. So that's a I use this example just to explain that, it's not being pedantic or trying to be very precise for just mathematical rigor. This actually means technically that you have, technically a tensor is the family of all equivalent basis expressions that they represented, right? And so those families are exactly distinct when your tensors are, in the matrix example, 1, 1, 0, 2, or 2, 0 in covariant, contravariant indices, right? So just to say that we are in a kind of less sophisticated world here. I'm saying forget linear algebra. We don't have linear algebra. We just have index arrays and the ability to multiply and sum the entries because they are numbers and they belong to some field of numbers or whatever. So we don't have linear algebra, so we have to invent it, basically. We have to like tell these arrays how to multiply together. We don't have default things to do with them, right? And that's where I'm going. So these contraction operations is what generalizes linear algebra. So for example, if let me see what is a good visualization here. Where do I have the matrix product? So okay, so let me tell you how this works. So index contract basically means that you specify a number of indices, you specify a number of indices that don't get contracted, and then the result is basically the array that you need to produce by summing over the indices that need to be contracted or need to be summed over as a thing. So this is matrix multiplication, right? In Mathematica, you can also do, I guess, matrix multiply. Is that no? Sorry.
Just dot. Just dot or array dot.
Array dot.
Yeah, that's a new thing actually.
Yeah. Oops.
It's comma 1. You just dot if you don't want to specify this argument. I think you're missing
So
something.
what are A, B? Are those vectors?
Yeah, these are matrices.
Oh, they're matrices.
Yeah. So let me just.
Can you print those out?
Yeah.
All right. Oh, no, they're.
Oh, because it renames to A. I think in some of
Oh.
these things we rename to A at some point. Sorry. That's why it was going wrong. Run this again. So yeah.
Now print out A if you could.
Yes. So A and B are just
Oh,
matrices.
Okay.
So I mean, if I just do A, B, do matrix. Right? These are just matrices. So this particular operation of index contract AB, it just gives you matrix multiplication, right? But if I take a bunch of a couple of objects with a bunch of indices, I can define a much more general thing. So here are some examples that I can define. Actually, let me just go.
Yeah, so let's see. So the IJ and the JK went to IK. That means that the I was contracted. Or no, I'm sorry, the J, the middle.
The J was contracted.
The middle.
That's right.
So the second index from the first argument and the first index from the second got contracted together. And that's typical matrix convention. Yeah. So
that's typical matrix multiplication. Yes.
Now, where I feel it might get tricky is like you have like a 3-dimensional array and a 3-dimensional array, and you say like I want to contract like the first and second on the first one, and then like you pick 2 here, you pick 2 there, and you don't know which two of those 2 and 2 which ones to contract with which ones, I guess. Or that's you have to specify that if you want to do things.
Yes.
Correct.
So that's exactly where we're getting into here. Say ternary products. Here's a bunch of options. There are many more.
Yeah.
But here's a bunch of interesting ones. Interesting for reasons that hopefully will be apparent in a moment. So if I specify ABC as my QBCs, right, cubic matrices, these 3 index objects, this contraction particularly works by doing it's trying to mirror matrix multiplication quite closely. So this is called the Zapata-Carratalá, the BM product. It's taking the third index from the first, the second index from the second, and the first index from the third. So mirroring that pattern you just spelled out for the matrix case. And it's contracting those. So IJK are left free. So crucially, P is repeated over, and because it does not appear here, it is contracted. So this gets very messy because you inspect quickly by eyesight all these expressions. They all look very similar, right? It's difficult to just by inspecting that these things are different because it's just a bunch of IJ, K's, P's, and all mixed together. So this representation is no longer optimal. So we developed this so-called this is the section. These so-called Plex diagrams. So Plex diagrams are just a way to identify products. So the way it works is each edge represents an array and each node represents an index, right? So if arrays share indices, they're going to be adjacent on the representation with the Plex diagram. And if arrays are if indices are contracted, we can graphically signify it with some kind of annotation. In this case, the convention is that the black nodes are the free indices. So you at a glance can just count the number of black dots and you know the order of your array, kind of the shape of your array. So you know that the end result of this thing and the end result of this thing doesn't matter what happens in the middle. It's the same kind of object. This is matrix multiplication, actually. It's just 1, 2, 2, 3. That's the index contraction pattern. And this is some kind of Cubix version of matrix multiplication where you're actually matching two indices that are in between in here, right? Like 1, 2, and 2, and 2, 3. So basically, so that's this option. And in the list of examples that we had above, this is the BM product. So this looks like much more analogous to this, right? If all you have to play with are sort of pairwise edges, binary edges. I mean, this is a natural diagram to form, right? Just put two together. That's basically the only thing you can do it in this minimal way. If you have three now ternary edges that represent these cubices, this is certainly an analogous way to do it. You put three together that form a triangle and just have one in common and others in the outskirts boundary. So this is representing the thing before, and I think I have it down here. When we go to Plex to product, so basically you specify the diagram as a hypergraph, and you say this is meant to be read as a product of arrays. Then we can check that indeed, we take this diagram as a Plex product, we say Plex to product, and we take two matrices AB as above, and indeed that is matrix multiplication. So similarly, we take the BM contraction of indices that looked a bit esoteric, all those contractions, and what this equality is telling you is that, hey, this is matching up. So to get the perspective of what's going on here, right? I wanted to use a Cubix form, so I can do Cubix form of for you to get a sense of what's going on here. So if I take the XYZ cubices here, you see that this is what the inputs are to this product, right? And if I just do the Cubix form of their product, so basically this side, then you get something like this, right? Mm-hmm. So this is what's going on here, right? So what's going on is that this Plex diagram is giving you a single Plex diagram. So actually, I didn't implement. This should be very quick. I don't know why it was perhaps so direct that I didn't do it myself. So basically, you could take any array and you could just represent it as a Plex diagram. I mean, it's as trivial as basically just taking the names of the indices and generating a hypergraph of that shape. So you can see that the input of this operation is a 3-index array 3 times, and the output is a single 3-index array, right? And this diagram captures it minutely, and so this is what's going on. So what is interesting, and another final thing that I wanted to show is that where is 3D Cubix visualization? No, I wanted to. Yeah, in contraction operations. Well, perhaps yes, here in ternary. Yes. So here's a bunch of properties. The reason why I called the partial identity arrays, it's because they behave as identities in some sense, right? So if you take, so I define ID as my tri-identity and red, green, blue as the partial ones. So the kind of the tri-identity is the white one, and the other ones are the RGB. You multiply them together, they give you the identity. So I think, in fact, that equation is somewhere. Where's for can we find it? Equation. Maybe this one didn't have it, but basically these are equations of the form one identity of these 4 equal to another identity of those. And you can see that there is, let's see, 1, 2, 3, 1. Interesting. Okay, maybe this product didn't have that, red, green, blue equals white, but some others did. But in any case, what's going on here is that, if I take, so let me show you what's going on. I mean, this is just a search to know what to try to render, but let's go to this. So what's going on here? So basically, I have, 3 times the identity equals the identity. That's similar to what happens with the usual matrix case, where identity squared is just identity. But also you have, where is the example? Where's the motivating example here? Oh, here. So for example, the partial identities, the red identity 3 times is also the red identity. That's an interesting one. But also the reason why we call these identities is that you take alpha. So alpha, we do Cubix form of this. Oh, sorry, alpha is symbolic. Let's just do a, x. Yeah, so we have this random integer array in x, right? And so if I put x here, this should still be true. Whoa, why? What's happening? Are IGB, they're integer? How come? That's very strange.
What does it output? Your BM product. By itself.
Oh, it's different. Oh, it's a different size. Okay. So, right. So these are size 2. Let me just make them size 3. Yeah, sorry. Exactly. So it's just different size. So yeah, so you can see that this applies to this one. So what's happening here is that I take this x, and so I put it together with, so I put it together with the green in the second argument and the blue in the third argument, which are these 3 arguments, right? So you can see that it's a bunch of like -1s and 2s and 0s here, and here's just like the 1s and 0s in this particular pattern. And what happens is that, after you make all the contractions, these complicated ways, you actually get back the exact same matrix, right? this is unaltered by this multiplication, and this is a fairly complicated process. So it's highly non-trivial that you know that by placing this matrices here, you get the exact same matrix, right? And it's very peculiar. So for example, I think the other one, I believe, the other equation that you can get is something like I red X I blue, if I remember. No, so maybe it's green here. Maybe it's blue here. Sorry, this is just blue. No, so for example, you get the equations are here. So 5 is, which ones have 5s? Here's a 5, 2 and 1. So red, so green and blue, green and red. Okay, so for example, you can get green here and red. Yeah, this one is true, right? So it's kind of, I mean, this list is the complete list of all the identities. But I wanted to kind of show you that it is kind of tricky. It's like it's no longer the simple life of the binary world where you just have one identity, multiply, do nothing, and carry on with your life. Here is like I have a ternary operation. I have 4 elements that are special, singled out because they are canonical. They're always there in QBCs. So if you give me a generic Cubix X, if I happen to place these arguments in this order of these specific kinds, I get an identity operation. So basically, Bhattacharya-Meissner product with green and red in first and third arguments acts like the identity map on QBCs, right? So anyway, just to give you some flavor of all this stuff and the fact that we have some nice functions now to visualize these things, and yeah. So of course, the natural thing that we carry on doing here was searching for axioms for these things. What kind of, because we know matrix multiplication is associative. What kind of associativity-like things happen? And this is a story for another time. This is not the scope of today. But yeah. Anyway, that's what I wanted to basically just show Cubix form in action. I don't know, Nick, if there was something that you would like to see that is possible that it didn't show. We already saw that there's nested stuff.
Well, I don't know. Pretty trivial function. I don't know. There's not much to show there.
Yeah, it's just a yeah.
The only amusing part is like putting a Cubix inside a Cubix. Like...
Yes, yeah, that's cool. That's very cool.
And you can click on it and see inside. I was going to make like a actual substitution, like a button. If you click on it, you replace the whole Cubix with whatever you clicked, and
right.
button to go back.
Right. So when you have, I guess when you have these like these ones, right? You just click this and I get the matrix. But if it's a Cubix, it's already in Cubix form, right? That's the point.
Yeah.
So if I do what is this?
Just
5, 6.
5, 6, 5, yeah.
Yeah, 6 here. So yeah, so this is a 2 by 2 by 2, 2 by 2 by 2 Cubix of integer values. And then, so of course you can see there's a Cubix of QBCs. So you can take one and you get that Cubix that is living there, right? That is super neat.
Yeah.
That's such a cool.
But it would be better if you just more interactive without like copy pasting it.
Yeah. Yeah, that's really cool. Like, that was the 2-2 entry. I can take the 1-1-2 entry here. That's the one.
So it recurses like that if you get like.
Yeah.
Where's what?
That's recursive then. The cube of cubes.
So this is just like when you say matrix form of like here, right? I said matrix form or something that is.
Yeah. But okay, if you did like integer 9 2 there. Try to break it. Oh well.
There's
Well, I
always
guess
a-
this could be,
Correct.
yeah, it works. So you
But
copy
no,
the
it should be like a cube, and then on those are cubes of cubes.
so
Cubes
this is
tiny.
Cubeception going on. We need to go deeper.
yeah. So but it's working well, right? Because there is a cube of like the outermost layer and the inner one, right? And that there's a cube, and the cube is made of these cubes, and then I can copy that one, and this one gives me a numerical one.
What? Oh, you copied it out of there. I see.
Yeah. So this one, I copied one entry that gave me this one, and then I copied one entry gives me this one. It's really cool. Like
Yeah.
it's that this is really the thing that should be displayed and learned because it's pretty cool. It's very simple. I agree, Nick. It's very simple, but it's very cool.
Well, we can still prove it. You haven't submitted it yet.
Yeah, I couldn't find
Completely.
it. I was looking for it. But,
Sure. Yeah, we can
um,
improve it.
but so like here's a question. Okay, let's say you have like a rank 3 tensor and a rank 3 tensor, and you want to say like I need to contract index 1 from the first with index 1 on the second, and then I need to contract like index 2 with index 2. So like you pick which indices here contract with which indices here. Does it matter the order of operations of you contract along this pair first and then contract along the second pair?
Absolutely. Yeah.
It does matter?
Absolutely. Yeah.
Uh-huh. Okay.
So in general, everything matters. Like there's no, I cannot say some like general blanket statement that tells you, oh yeah, you can forget about this or that order. Like everything matters when you do in these operations.
Mm-hmm.
Like, you can, if you alter the index order, the internal order, I mean, like that's like applying index permutations. If you change the argument order, everything is going to change the output in general, right? So another
when they write it out, it's like an Einstein notation. Is it Einstein notation or Eisenstein? It's Einstein.
Einstein.
Okay.
Einstein when there's the contractions. Yeah.
So like you have like the curvature like this, you have like R, and it has like 4 indices, and 2 of them are up. And then you like that, you product that with some other tensor.
Yeah.
And like 2 of them are down. And so you know that like these 2 are going to be paired with these 2, but you don't know like the order, I guess. I mean, you have to rely on convention to like map it out.
Yeah. Well, in Einstein's convention, you have a sequence of indices,
Mm-hmm.
and so when you name them, right? They always have unique names. Because I mean, if they are repeated with the same name, it means that you're taking some kind of diagonal, right? So they have unique.
It's like
and they have a
alpha is
sequential.
up here, then in the next one, alpha is down there, and you know that.
Yeah.
Uh-huh.
So yeah, I mean those things are essentially they operate like, like ports essentially. Like you have this sort of like this tensor network representation, where you have like many to many things, and you're just like doing several from this one, several from that one, like that. That's what tensor contractions in usual, multilinear algebra look like. But these things look like this Plex diagrams, right? Like the Plex diagram is what, and the Plex diagram might have internal symmetry, right? Like it might have, where is it? Yeah, it might have like these things are actually ordered inside. So they have there is some internal directionality because index 3, 4, and 2 are in a specific order and so on. So they kind of look like directed hypergraphs to faithfully represent the actual array operations. So anyway, it's a big mess. Like this is a big mess. I mean, my whole research effort in the last few years was to try to make sense of this, and and this is, I think people have heard it before in the audience and here in the institute, but this is what brought me to the institute originally. The fact that I was dealing with this big mess of indices with the arrays themselves or the tensors themselves, and I was like writing diagrams for myself to like keep track of things because it was a big mess. And then slowly I realized, wait, I'm drawing diagrams with hypergraphs. And so I went out and there was this group of people doing hypergraphs already. I was like, huh, maybe there's something here. So it was kind of this narrative, right? Like it came from this. Hypergraphs seem to be super relevant here, and I mean, I guess history in the making. We are now writing a grant where we're explicitly saying, hey, we want to study these hypergraphs for physics and space-time like things, but also for this pure mathematical stuff, right? So anyway, it's just to highlight that this is kind of moving along, and we have one soon we're gonna have something that is quite unified. You know, have the hypergraph backlit dealing super well with all these rules, and we have this very seamless transition between whether you talk about the adjacency tensor of a hypergraph or the Cubix or something. You know, these things can be neatly translated. I feel like that we're in a moment where these formal languages are they're very rough because it's new to all of us, but we're clearly going in a direction where these things become kind of more standardized or more familiar. And because, you know, a hypergraph and an adjacency tensor are essentially the same thing, right? It's just a matter of how you want to visualize it or represent. And the fact that there's this canonically defined operations on arrays that are represented as well with hypergraphs gives it some sense of sort of self-reference in, at least in the representation sort of aspect. And yeah, it's kind of what we are into. So we'll keep on updating in this direction. We'll see what comes out of it.
Great, awesome.
All right, everyone. So that's what I had on my end.
All right, thank you, Carlos.
Yeah, thank you, everyone. And I guess we'll see you on the Discord. If you haven't joined, make sure to find our community and links and everything on our website. And yeah, there's a lively conversation going on. So welcome everyone there. And yeah, Dugan and Nick, have a good weekend.
You as well. Bye, guys.
Yep. Have a nice weekend.